Dear students, in the previous classes we have discussed the concept of economic profit as distinct from accounting profit, and also the cost minimizing input choice by a competitive firm. Cost minimizing input choice by a competitive firm. In the present class, we will consider this input in this cost minimizing input choice and the corresponding expansion path with the Cobb-Douglas production function and CES production function. Now first we consider the cost minimizing input choice with respect to Cobb-Douglas production function and the nature of the expansion paths generated by Cobb-Douglas production function. We know that the Cobb-Douglas production function is given as L raised to beta. So the problem is maximize subject to WEL plus RK is equal to C bar. WEL plus RK is equal to C bar. So we formulate the Lagrange function as WEL plus RK plus lambda into C bar minus WEL minus RK. And subject to maximize, the problem we write it as minimize cost, minimize C is equal to WEL plus RK subject to Q is equal to A K raised to alpha L raised to beta, because the objective, the constraint and objective function are specified here. So the Lagrange function is WL plus RK plus lambda Q minus A K raised to alpha L raised to beta. We are considering the cost minimization problem. You will get the same result if you do the output maximization problem. Both will give you identical results. Then dou phi by dou k is equal to R minus lambda into alpha A K raised to alpha minus 1 L raised to beta equated to 0. Dou phi by dou L is equal to W minus lambda beta A K raised to alpha L raised to beta minus 1 is equal to 0. Dou phi by dou lambda is equal to Q minus A K raised to alpha L raised to beta. Now, from the first two equations, you will get W by R as equal to W by R as equal to, that is dividing the second with the first, as equal to alpha by beta, a, lambda, etc. will be cancelled. K raised to alpha, k raised to alpha, L raised to beta. Alpha by L by, sorry, K by L. K raised to alpha, W by R. So, K by L into K by L. This is the result we have derived earlier. W by R is equal to alpha by beta into K by L, or K by L is equal to W by R into beta by alpha. K by L is equal to W by R into W by R into W by R is equal to alpha by beta into beta by alpha into K by L, so that K by L is equal to W by R into alpha by beta. This is the result which we have derived for the expansion path in the Cobb-Douglas case. So the same can be derived like this also. And we know that this beta by alpha into K by L is the MRTS, marginal rate of technical substitution, MRTS. Beta by alpha, this W by R is the factor base ratio, and the condition for equilibrium is MRTS is equal to W by R. So beta by alpha into K by L is the MRTS, MBL by MBK, that you will obtain from the result. And solving for K by L, you will get K by L is equal to W by R into alpha by beta. Now, it is clear that the cost is minimized when the ratio of input prices W by R is equal to MRTS. The ratio of input prices is equal to MRTS. Now, as I have told you earlier, if a production function is homogeneous, the expansion path generated by such a production function will be a straight line. It means that when the firm expands the scale of operation, purchasing more units of capital and labor, capital labor ratio will remain the same. Capital labor ratio will remain the same. And capital labor ratio is equal to W by R into alpha by beta. And we know that alpha and beta are constants. Then the question is, what about W by R? In a competitive economy, where the firm is purchasing labor and capital from a competitive factor market, whatever amount of labor and capital is purchased by the firm, W by R will remain the same. So the point is, as long as W by R is a constant, W by R is a constant, K by L will remain a constant. So when the firm increases the scale of operations like this, it will move to successively higher isocons, and the expansion path, let it be OE, the expansion path will be a straight line. And this is true for all homogeneous production functions. All homogeneous production functions. So in the Cobb-Douglas production function, expansion path is a straight line because Cobb-Douglas production function is homogeneous. Now let us consider a concrete example. Let alpha is equal to beta is equal to 0.5 and W is equal to 12, R is equal to 3, and also assume that is equal to 4. That is, the level of output is represented by Q0 equal to 40. Now the question is, which combination of capital and labor produces 40 units of output with the minimum cost? To find out this, the equilibrium condition is W by R is equal to beta by alpha into K by L, and K by L is equal to W by R into alpha by beta is equal to 12 by 3 into 0.5 by 0.51. So K by L is equal to 12 by 3, 4. So that K is equal to 4L. And if you substitute this value in the production function, Q0 is equal to 40 is equal to K raised to 0.5, L raised to 0.5 is equal to 2L is equal to, how it is written as, this is equal to, K is equal to 4L. So 4L raised to 0.5, L raised to 0.5, that will give you, this value is 2L. 4 raised to 0.5, then L raised to 0.5 into L raised to 0.5 L. L raised to 0.5 2L. And here the intercept A is ignite. I simply write it as K raised to alpha, L raised to beta. So Q040 is equal to 2L. That means 40 is equal to 2L. And L is equal to 20, and K is equal to 4 into L. L is equal to 4 into 20, 80. So total cost is equal to 3 into 80, that is WL plus RK, 3 into 80 plus 12 into 12, 20 is equal to 480. The cost of producing an output equal to 40 is 480 when the firm uses L equal to 20, K equal to 80, which is the least cost combination of inputs to produce the level of output 40. Now, this Q is equal to 40 can also be produced by K is equal to 40, L is equal to 40. Then the problem is C will be 600. That is, Q is equal to 40 raised to 0.5, 40 raised to 0.5. That is root 40 into root 40 is equal to 40 Q. And if you substitute Q is equal to 40 K, 40 L, 40 here, 3 into 40 plus 12 into 40 is equal to 120 plus 480, it is 600. Any other combination of K and L give you, any other combination of K and L will give you a higher cost than 480. And this is the point where the isocont is tangent to the isocost line. Isocont is tangent to the isocost line. Total cost is 480. So this isocost line represents, this point represents a cost of producing output 40 with 480. Any other combination of capital and labor will give you a higher cost compared to this. Now, let us see the results with respect to CES. With respect to CES. We have earlier defined the RTS for the CES production function as 1 minus alpha by alpha into k by L raised to 1 plus beta. And cost minimization requires that W by R is equal to RTS. That is, W by R is equal to 1 minus alpha by alpha k by L raised to 1 plus beta. And it follows that k by L raised to 1 plus beta is equal to W by R into alpha by 1 minus alpha. So that k by L is equal to W by R into alpha by 1 minus alpha raised to 1 by 1 plus beta. Beta is greater than minus 1. If you formulate the Lagrange function, you will get W by R as equal to this. For convenience, I write it like this. You will get W by R is equal to, if you formulate the Lagrange function with the CES production function, you will, and differentiating, you will get W by R is equal to this. I directly write it because we know what is RTS. So k by L is equal to W by R into alpha by 1 minus alpha. And like a Cobb-Douglas production function, CES production function is also homogeneous. That we have, that is something which we have already proved. Now, if beta is equal to 0, this becomes 1 by 1. Then k by L become W by R into alpha by 1 minus alpha. And alpha by 1 minus alpha, or alpha by beta in the Cobb-Douglas case, constant. Then k by L here also depends on W. So stated differently, W by R is a constant, alpha by 1 minus alpha is also a constant. And as long as W by R is a constant, K by L is a constant. So naturally, the expansion path generated by the CES production function, like the Cobb-Douglas production function, is a straight line. Expansion path is a straight line. Now, if W by R is not a constant, if W by, remember this, our expansion path analysis is based on the assumption that factor prices are constant. That is why iso-cost lines are drawn as parallel to one another. If W by R is not a constant, And we know that 1 by 1 plus beta is sigma. So I simply write it as W by R into alpha by 1 minus alpha raised to sigma, because sigma is 1 by 1 plus beta. Now if suppose that and one more point, in the Cobb-Douglas production function, the cost minimizing K by L ratio changes in proportion to W by R. If sigma is equal to 1, that is the Cobb-Douglas case. In the Cobb-Douglas case, K by L changes in proportion to W by R. As long as W by R is a constant, K by L will remain constant. That is the case of sigma is equal to 1. That is beta is equal to 0. If sigma is greater than 1, if W by R changes, there is a what to say, greater than proportional increase in the cost minimizing K by L ratio. If sigma is greater than 1, cost minimizing K by L increases more than proportionately to W by R. If sigma is less than 1, cost minimizing K by L increases less than proportionately to W by R, provided that W by R is not a constant, it is a variable. So if sigma is greater than 1, the response of K by L to W by R is more than proportionate. If sigma is less than 1, the response of K by L to W by R is less than proportionate to 1. Remember these points. In the Cobb-Douglas production function, there is, as sigma is equal to 1, the proportionate response of K by L is always same as the proportionate response of W by R, because this is equal to 1 by 1 plus beta. Because beta is 0, we have sigma is equal to 1. So this is how we represent cost minimizing input ratio and also the corresponding expansion paths in the Cobb-Douglas and the CES case. And remember this, as long as W by R is a constant, expansion path generated by the Cobb-Douglas and the CES is a straight line. When W by R changes, in the Cobb-Douglas case, K by L change in the same proportion. But in the CES, it change in the same proportion, more than proportion, less than. 3 possibilities are there, depending on the value of elasticity of substitution. And Cobb-Douglas is, as we have seen earlier, only a special case of CES. That is the cost minimizing examples from Cobb-Douglas and CES.